with its imposing delta wings spanning over 100 feet, merged seamlessly with a streamlined fuselage into a sleek and daunting celestial arrow, the XB-70 Valkyrie, a 243-ton, 196-foot-long superbomber, was decades ahead of its time in the 1950s when it was brought to life by North American Aviation. The Valkyrie's wingtips, ingeniously designed to fold downwards in flight, lent it a predatory grace, and it was meant to be a predator, a supersonic nuclear-armed harbinger of destruction. It was designed to glide across continents to the very heart of Moscow and rain down atomic annihilation. Soaring at Mach 3 with an operational ceiling that broke into the stratosphere at 77,350 feet, the Valkyrie was untouchable. No enemy plane or defensive system could intercept it at such speeds and altitudes. In the grip of the Cold War, it stood as the ultimate trump card, an unassailable warplane. But creating such epic aviation engineering soon spiraled into a labyrinth of challenges: technical nightmares, exploding budgets, and a relentless Soviet Union hell-bent on outpacing the United States at every turn. As the Valkyrie stepped up to claim its destiny, however, the Soviets unveiled an unforeseen and revolutionary countermeasure that threatened to turn the entire program upside down. In the early 1950s, the U.S. had a rather unconventional problem. It had a growing arsenal of nuclear bombs, the most powerful weapon known to man, but it had no reliable way to deliver it all the way to Soviet Russia if the rivalry between both superpowers escalated into an all-out war. At the time, nuclear weapons could weigh several tons, and the need to take enough fuel to fly that payload from the continental United States to the Soviet Union demanded incredibly massive bombers. In 1955, the Air Force issued General Operational Requirement No. 38 for a new bomber to solve this issue, combining the payload and intercontinental range of the B-52 with the Mach 2 top speed of the Convair B-58 Hustler. The U.S. Air Force's Air Research and Development Command, or ARDC, was seeking a bomber that could maintain a cruising speed close to the speed of sound and reach the highest possible speed for short bursts during a 1,000 nautical mile approach and departure from its target. Like a long-distance runner who maintains a steady pace but can sprint when needed, the bomber was required to rush into and from its target. Additionally, the bomber was required to carry a massive payload of 50,000 pounds, the weight of 6 elephants, and have a staggering combat radius of 4,000 nautical miles, roughly the distance from New York to Rome. This combination of speed, payload, and range was unprecedented. As these specifications were drawn up, the realm of supersonic propulsion was undergoing revolutionary advancements. North American aviation was at the forefront, poised to not just meet, but shatter these lofty Air Force expectations. In their quest for superiority, North American aviation delved deep into every scrap of aeronautical research. This led them to a little-known 1956 treatise by a pair of National Advisory Committee for Aeronautics wind tunnel savants titled Aircraft Configurations Developing High Lift-Drag Ratios at High Supersonic Speeds. Today we recognize this concept as compression lift, harnessing the shock wave emanating from the aircraft's nose or other acute angles to generate a pressurized airstream. By astutely aligning the wings with this shock wave, the aircraft could capture the shock's intense pressure underneath the wings, creating extra lift and rewriting the rules of supersonic flight. The result would become the XB-70 Valkyrie, the prototype version of the requested B-70 supersonic bomber aircraft designed to serve as a deep-penetration strategic bomber armed with a nuclear arsenal. More significantly, it would be faster than Mach 3, over 3 times faster than regular bomber aircraft. As if that were not enough, North American engineers once toyed with transforming the Valkyrie into the world's inaugural nuclear-powered warplane. This idea emerged shortly after the United States Air Force requisitioned the aircraft. The engineers didn't just draft plans for a conventional version powered by afterburning turbojet engines. They delved into nuclear propulsion. These nuclear ambitions materialized as the Weapon System 125A, a designation that marked a serious foray into atomic-powered flight. The XB-70 Valkyrie was on the cusp of entering this uncharted territory. The engineering teams harnessed the General Electric J-47 turbojet engine to craft 2 nuclear aircraft engine prototypes. Pushing the envelope, they managed to fire up these engines to near full thrust using dual-shielded reactors in a groundbreaking test of ingenuity. However, this initial triumph soon collided with harsh realities. The staggering cost of developing a nuclear-powered aircraft became apparent, casting a shadow over the project. Moreover, the inherent risks of airborne nuclear reactors, a Pandora's box of safety concerns, loomed large. Faced with these daunting challenges, the nuclear-powered aircraft concept, including the Valkyrie's atomic variant, was grounded. Yet the echoes of this venture linger. The nuclear engine prototypes, HTRE-2 and HTRE-3, stand as tangible relics of this ambitious era. No longer shrouded in secrecy, they now bear silent testimony to a bold vision at the Idaho National Laboratory, accessible to the public and history enthusiasts alike. The North American XB-70 Valkyrie, though it never realized the ambition of becoming the first nuclear-powered warplane, stood as the zenith of modern engineering within the aerospace industry. This awe-inspiring aircraft pushed the boundaries of aeronautical design and functionality, even in its conventionally fueled version. One of the Valkyrie's most distinctive features was its delta wing, seamlessly integrated into a slab-sided fuselage that housed its 6 powerful jet engines. The Valkyrie's wings were engineered with a pioneering spirit. The outer panels of these wings were hinged, a design choice that significantly enhanced the aircraft's performance across different flight conditions. During takeoff, landing, and when flying at subsonic speeds, these wing panels would remain horizontal, augmenting the lift generated by the wings and thereby improving the lift-to-drag ratio. A dramatic transformation occurred in supersonic flight. The wing panels would hinge downward. This adjustment mitigated the drag typically caused by the wingtips interacting with the inlet shock wave, optimizing the aircraft's performance at high velocities. The Valkyrie's cockpit was the epitome of innovation and sophistication, designed with a unique outer windshield and ramp mechanism to maximize pilot visibility, a critical factor during low-speed, nose-high flight and ground operations. This mechanism allowed for a 2-mode operation. When lowered, the ramp enabled the pilot to peer through the fixed cockpit windshield, a feature indispensable for takeoffs, landings, and low-speed maneuvers. Conversely, when the ramp was raised for high-speed flight, it seamlessly blended into the aircraft's forebody, streamlining its shape and thus bolstering its aerodynamic efficiency at blistering speeds. Additionally, the Valkyrie addressed the challenges of rain removal and windshield anti-ice by utilizing hot bleed air from the engines, heated to around 600 degrees Fahrenheit. This system ensured clear visibility and safety in various weather conditions. The General Electric YJ-93 GE3 turbojet engine, used in the XB-70 Valkyrie bomber, was a notable example of advanced aero engineering from its era. This engine was distinctive for its high-pressure, variable stator design, which allowed it to operate efficiently at high speeds and altitudes. It could reach speeds up to 2,000 miles per hour and fly at altitudes around 70,000 feet. The engine's performance characteristics included a maximum thrust of 30,000 pounds with an afterburner and 22,000 pounds without an afterburner. It also featured an 11-stage axial flow compressor with variable stators and a 2-stage axial turbine, contributing to its impressive thrust-to-weight ratio above 5:1. This high thrust-to-weight ratio means the engine could deliver over 5 times more thrust than the weight of the aircraft, ensuring exceptional acceleration and agility. The YJ-93 GE3 was explicitly designed to run on JP6 fuel, a special high-temperature jet fuel developed to meet the demanding requirements of high-speed, high-altitude flight. The engine weighed 4,770 pounds, a relatively lightweight design considering its power output and capabilities. This engine played a crucial role in the XB-70's performance, contributing to its ability to cruise at Mach 3.2. In the tense climate of the 1950s Cold War, the North American XB-70 Valkyrie was envisioned as the ultimate strategic weapon. Military strategists of the era believed that a bomber capable of achieving such high speeds would be nearly invulnerable to the primary defensive measure of the time: intercepting fighter aircraft. The B-70 Valkyrie's design promised to outpace any incoming threat, effectively vanishing from hostile skies before any danger could draw near. Its ability to soar to an impressive service ceiling of 70,000 feet further enhanced this advantage, as it could operate at altitudes beyond the reach of contemporary enemy fighters. Additionally, the Air Force anticipated that the Valkyrie's high-speed capabilities would enable it to swiftly escape the blast radius of the nuclear payloads it was designed to deploy. Even without incorporating stealth technology into its design, the B-70 posed a formidable challenge for enemy radar systems. Its blistering speed meant it would appear on radar screens only briefly, significantly limiting the time window for an enemy response. Sometimes the bomber might not even register on radar, depending on specific conditions. But suddenly everything came crashing down. The initial promise of the XB-70 Valkyrie, conceived in an era where intercepting fighter aircraft and anti-aircraft artillery were the primary defenses against bombers, began to unravel with the advent of new military technology. While anti-aircraft guns had limited effectiveness and fighter aircraft increasingly struggled to keep pace with advanced bombers, a new threat emerged that would drastically alter the strategic landscape: the advent of Soviet surface-to-air missiles, notably the SA-2 guideline. This new missile technology raised severe doubts about the XB-70's ability to evade such advanced defenses, directly challenging its primary strategic role. The Valkyrie's impressive Mach 3 speed, once considered its shield against interception, no longer guaranteed its survivability in the face of these potent weapons. In response to this heightened threat, the United States Air Force adapted by flying missions at lower altitudes, where it was more difficult for enemy radar to detect and track the aircraft. However, this tactical adjustment came at a significant cost to the XB-70's effectiveness. At lower altitudes, the Valkyrie's performance advantages diminished, rendering it less effective than the B-52 Stratofortress, the very bomber it intended to surpass. Additionally, operating at lower altitudes adversely affected the aircraft's range and fuel efficiency. Compounding the XB-70's challenges was the development of intercontinental ballistic missiles, or ICBMs, in the late 1950s. The Valkyrie had been specifically designed to deliver heavy nuclear payloads, a role now increasingly being fulfilled by these ICBMs. The rapid advancement in missile technology not only threatened the Valkyrie's strategic role, but also called into question the necessity of such a bomber in the evolving context of nuclear warfare. The emergence of intercontinental ballistic missiles dealt a further blow to the XB-70 Valkyrie program. During the Valkyrie's development, significant strides were made in missile technology. These missiles presented a more cost-effective and reliable alternative for delivering nuclear payloads. This technological shift began to render the concept of a high-speed, long-range bomber like the XB-70 increasingly redundant, especially in the face of the strategic and economic advantages offered by ICBMs. The new tendencies became evident in the decision of the Kennedy administration to discontinue plans for deploying the B-70 bomber in an operational capacity. However, the story of the Valkyrie was not yet over. Even though the XB-70 Valkyrie program was officially canceled, 2 prototypes were constructed not for combat but for experimental purposes. These prototypes became crucial in testing the aerodynamics, propulsion, and other characteristics vital to understanding sizable supersonic aircraft. Coinciding with the program's cancellation was a burgeoning interest in supersonic transport, or SST, within the American commercial aviation industry. The XB-70 Valkyrie, with its advanced design and features, emerged as an ideal platform for SST research. Its size was comparable to the projected designs, utilizing similar structural materials, such as brazed stainless steel honeycomb and titanium. This alignment of features transformed the XB-70A from a prototype of a manned bomber into one of the most significant research aircraft of its time. The first XB-70 took to the skies in September 1964. It achieved the milestone of Mach 3 flight in October 1965, showcasing its incredible capabilities. The second prototype followed, making its first flight in July 1965. But just as the XB-70 Valkyrie was beginning to carve out a new role for itself in aviation history, a catastrophic incident on June 8, 1966, cast a shadow over its legacy. The tragedy occurred during a promotional photo shoot organized by General Electric, the aircraft engine manufacturer. XB-70, a number 2, was part of a formation that included an F-4, F-5, T-38, and an F-104. In the aftermath of the photo session, the F-104, piloted by NASA's chief test pilot Joe Walker, inadvertently drifted into contact with the XB-70's right wing. The F-104 flipped over and collided with the Valkyrie in an inverted roll. It struck the XB-70's vertical stabilizers and left wing before exploding. This catastrophic collision wreaked havoc on the Valkyrie. It lost its rudders and sustained significant damage to its left wing, leading to an uncontrollable spin that culminated in a crash near Barstow, California. The accident claimed the lives of Joe Walker and Carl Cross, the XB-70's co-pilot. Al White, the pilot of the XB-70, managed to eject but suffered severe injuries. This incident, heart-wrenching in its own right, combined with the evolving strategic priorities in military technology and the rise of missile capabilities, effectively sealed the fate of the XB-70 Valkyrie as an operational aircraft. The remaining XB-70 prototype continued its flights, contributing valuable data for aviation research until it was eventually retired to a museum in 1969. The story of the XB-70 Valkyrie, marked by ambition, innovation, and ultimately tragedy, remains a bittersweet chapter in the annals of aviation history. It was the last of the gunfighters. In many other ways, America's Vought F-8 Crusader represented a departure from the conventional. Its strikingly unorthodox figure, characterized by its unique variable incidence wings and sleek silhouette, challenged the status quo with its innovative design. Its futuristic features made the Crusader a beauty to behold and a beast in performance, shattering expectations by becoming the first jet fighter in American service to break the 1,000 miles per hour barrier in level flight. In its reconnaissance role in the 1962 Cuban Missile Crisis, the F-8 Crusader helped avert nuclear annihilation. The F-8 then went on to prove its mettle as a tenacious dogfighter against the MiG-17 and MiG-21 in the turbulent skies over Vietnam, racking up the best victory ratio of any U.S. aircraft type during the war, as well as demonstrating its capabilities for devastating ground attack missions. This enduring legacy is crowned by its remarkable achievement of 20 years of service, a testament to its exceptional design and versatility in an era when Navy fighters were frequently replaced. The origins of the Vought F-8 Crusader stem from the issuing of a requirement for a new fighter by the U.S. Navy in September 1952, in the midst of the Korean War. The star of Communist North Korea's Air Force was the Soviet-built MiG-15, a highly advanced fighter that was faster, more robust, and better armed than most of its American counterparts. In order to stand a chance against this tough opponent, the Navy knew it needed an aircraft with higher velocity and deadlier weapons. To this end, the requirement demanded a top speed of at least Mach 1.2 at an altitude of 30,000 feet, with a climb rate of 25,000 feet per minute and a maximum landing speed of 100 miles per hour. It also stipulated the rejection of the .50 caliber machine guns used by many U.S. fighters of the day in favor of more powerful 20mm cannons, which the Navy was already using in its other aircraft. Stepping up to the challenge, aircraft manufacturer Vought got to work designing a carrier-based fighter to fit the Navy's specifications. Spearheaded by John Russell Clark, Vaught's design team chose a distinctive approach for their fighter, initially known as the V-383. Its wings were mounted much higher than usual, improving lift and stability and allowing for greater clearance between the aircraft's fuselage and the carrier deck during takeoff and landing, reducing the risk of damage. This configuration also facilitated the storage of larger, more effective landing gear within the fuselage, crucial for the harsh landing conditions experienced on aircraft carriers. However, the most interesting thing about the fighter's wings was not their placement, but the fact that they had an adjustable angle of incidence relative to the fuselage. Known as a variable incidence wing, this groundbreaking design enabled the wing to pivot upwards by 7 degrees during takeoff and landing without tilting the entire aircraft upwards, improving pilot visibility during these critical phases and ensuring a slow, safe landing speed. At the same time, the wings allowed for the downward adjustment of their leading-edge flaps by 25 degrees and the extension of their inboard flaps to 30 degrees, changing their aerodynamic shape to further enhance the aircraft's lift. In addition, Vaught's design incorporated several other state-of-the-art features, including a fuselage designed with area ruling for reduced drag at transonic speeds, fully movable horizontal tail surfaces known as stabilators for pitch control, notched wing edges to improve stability during turns, and extensive use of titanium to strengthen its structure without adding unnecessary weight. The aircraft was powered by a Pratt & Whitney J57, one of the first successful axial flow turbojet engines. Unlike earlier designs in an axial flow engine, air flows parallel to the axis of rotation, which allows for a more compact engine structure and efficient airflow dynamics, resulting in higher compression ratios and greater thrust. The engine also came equipped with an afterburner, a device that injects fuel directly into the exhaust stream of the engine, igniting it to provide additional thrust. This feature was particularly useful for military aircraft, providing a significant boost in power when needed, such as during takeoff from aircraft carriers, rapid climbs, and in combat situations requiring high-speed maneuvers. Meeting the Navy's armament requirements, Vaught's proposal was outfitted with 4 20mm autocannons as its main weaponry, capable of firing explosive shells as well as solid projectiles at a rapid rate. These cannons meant that the fighter would not only be effective against airborne opponents, but could also be used for strafing runs against ground targets. The aircraft was also equipped with a retractable tray capable of holding 32 unguided Mark IV Mark 40 folding fin aerial rockets, nicknamed Mickey Mouse rockets. Despite being small and unguided, these could be fired in rapid succession, and when launched in volleys, they could saturate a target area, increasing the likelihood of a hit on the intended target. The retractable tray mechanism was a novel idea that allowed for the storage of the rockets within the aircraft's fuselage, keeping them aerodynamically stowed until needed, helping maintain the aircraft's sleek profile and reduce drag. What's more, for increased air-to-air combat abilities, Vaught's fighter was also designed to carry 2 infrared-guided AIM-9 Sidewinder missiles, renowned for their ability to lock on to the heat signature of enemy aircraft by seeking out the target's engine exhaust, allowing the pilot to engage opponents beyond visual range and without the need for precise aiming that guns require. For extra aerodynamic efficiency and to minimize interference with the aircraft's radar and other systems, these were mounted on special points located near the cockpit area on the sides of the aircraft's fuselage, called cheek pylons because they somewhat resembled cheeks. These pylons allowed for quick and easy attachment of the missiles, ensuring that they could be deployed rapidly in battle. This impressive design would help propel Vaught's proposal to victory, winning the Navy contract in May 1953. With the aircraft now given the official designation F-8U-1, Vaught received an order for 3 prototypes the following month. Confidence in the success of the first prototype was extremely high by the time it took to the skies on March 25, 1955, so much so that pilot John Conrad even broke the sound barrier during the aircraft's maiden flight. The development process of the aircraft went smoothly, enabling both the second prototype and the initial production model of the F-8U-1 to take to the skies for their maiden flights on the same day, September 30, 1955. 1956 would prove a milestone year for the F-8U-1, beginning with the successful completion of its inaugural catapult launch from the USS Forrestal on April 4th. Meanwhile, armament development took place at the Naval Air Weapons Station China Lake in California, where on August 21st, Commander Duke Windsor achieved a level flight speed of 1,015.428 miles per hour. While this record did not surpass the world speed record held by the British ferry Delta, 2 since March 10, 1956, it did set a national speed record in the USA, surpassing a previous mark of 822 miles per hour set by an F-100 from the Air Force. Rounding off the year's successes, the aircraft's development team was awarded the prestigious Collier Trophy, an annual award given by the National Aeronautic Association to recognize the greatest achievement in American aviation design. However, instead of resting on their laurels, the team continued working hard on the aircraft's development. Before long, they had adapted an early version of the F-8U-1 Crusader for photo reconnaissance by fitting it with photographic equipment instead of traditional armaments, creating the first F-8U-1P. On July 16, 1957, Major John H. Glenn, Jr., a Marine Corps pilot, made history in an F-8U-1P by flying across the United States from California to New York at supersonic speeds, completing the coast-to-coast journey in 3 hours, 23 minutes, and 8.3 seconds. With the assignment of the F-8U-1 to various units from late 1956 onwards, its operational use would begin aboard USS Franklin D. Roosevelt in April 1957. Before long, it would also join VF-32 at NAS Cecil Field, Florida, which became the first fleet squadron to pilot the aircraft. Deploying on USS Saratoga to the Mediterranean later that year, VF-32 called its F-8U-1 squadron Swordsman, a reference to the aircraft's official Crusader nickname, which was now in use. Soon enough, more and more units in various theaters were forming Crusader squadrons, which typically took on the role of day fighters. Despite rapid advancements in engines and avionics leading to frequent updates in the aircraft used by Navy carriers, the Crusader became the first post-Korean War fighter to successfully carve out a more lasting place within the fleet, enjoying a notably extended service period. Meanwhile, the French Navy also incorporated a slightly modified version of the Crusader into its fleet. In September 1962, the Defense Department unified aircraft designation systems in line with the Air Force's approach, leading to the F-8U's rebranding as the F-8, with the original F-8U-1 becoming known as the F-8A and the F-8U-1P reconnaissance aircraft becoming the RF-8A. This latter model hit the headlines the following month for its significant role in the 13-day standoff between the United States and the Soviet Union, known as the Cuban Missile Crisis, which brought the world to the brink of nuclear war. Having proved their adeptness at taking detailed photographs at low altitudes, several RF-8As flew a series of highly dangerous low-level photo reconnaissance missions over Cuba, managing to record evidence of Soviet medium-range ballistic missiles on the island. This provided U.S. President John F. Kennedy with undeniable proof of the enemy's activities, which would be crucial for the tense diplomatic negotiations that followed. The world breathed a sigh of relief as the crisis eventually ended on October 29, 1962, with the Soviet Union agreeing to withdraw the missiles, a process that was also overseen by RF-8As. For their part in helping to narrowly avoid the catastrophic consequences that a further escalation of the conflict could have entailed, the pilots who performed these missions were awarded Distinguished Flying Crosses, while the units they belonged to were recognized with the prestigious U.S. Navy Unit Commendation. Less than 3 years later, as U.S. military presence in Vietnam increased, the F-8A would finally get its first taste of combat. While some believed the age of the dogfight was over, suggesting that air-to-air missiles would eliminate opposing aircraft long before they could get near enough to engage in close-quarters combat, this theory was soon proved wrong. On April 3, 1965, U.S. Navy Crusaders from USS Hancock took on a North Vietnamese fighter squadron, marking the first of many clashes over the Southeast Asian skies in the tumultuous years that followed. Though the Crusader had been created to rival the MiG-15, the North Vietnamese were now flying the more advanced MiG-17. To add to the challenge, the Crusaders often had to engage with the agile MiGs without the advantage of radar-initiated contact. Instead, pilots depended on ground-based controllers to locate the enemy and guide them to strategic attack positions. Typically, missions involve two F-8 fighters, with one pilot handling radar and navigation while the other visually scanned for threats. Directed by ground control to unsuspecting enemy fighters, they'd swiftly move in for the attack. Meanwhile, the constant threat of U.S. surface-to-air missiles would force the MiGs to fly at lower altitudes, where the F-8's superior maneuverability gave it an edge. As the war advanced, the F-8 Crusader would come up against an even more advanced opponent, the MiG-21. Nevertheless, effective teamwork and strategic exploitation of the Soviet-built fighters' vulnerabilities allowed the F-8 to remain a competent adversary in aerial combat, as proven on August 1, 1968. In the chaos of battle, notorious North Vietnamese flying ace Nguyen Hong Nhi attacked a pair of Crusaders using R-3 anti-aircraft missiles, managing a direct hit on one before going after the other. As the two fighters were locked in an intense dogfight, another two F-8S arrived on the scene to rescue their comrade. As the MiG received a deadly blow from a Sidewinder missile, Nguyen was forced to eject. The downing of the ace was credited to Lieutenant McCoy of VF-51 from USS Bonhomme Richard. Interestingly, most of the F-8's other victories in Vietnam were also achieved with its Sidewinders. Despite its famous Last of the Gunfighters nickname, only 4 enemy aircraft were taken down using its 20mm cannons, which often suffered from a jammed feeding mechanism. With the end of Operation Rolling Thunder later that year, the dogfighting period of Vietnam essentially ended, leaving the Crusader with the war's best victory ratio of any U.S. aircraft, downing 16 MiG-17 and 3 MiG-21 fighters to give a total of 19 against just 3 losses. As the Vietnam War dragged on, the F-8 took on a new role as a bomb truck, focusing its attacks on ground targets instead. At the same time, back in the United States, the Crusader caught the attention of NASA, which used modified versions of the aircraft to test some of its most groundbreaking new technologies. These included digital fly-by-wire systems, which utilized processing equipment from the Apollo guidance computer, and supercritical wing designs that later contributed to advancements in aircraft performance and efficiency. With the Vietnam War finally coming to an end in 1975, the U.S. Navy retired its last Crusader fighter models the following year, marking the end of nearly 20 years of service, a new record for the longevity of a Navy fighter. Many of the retired F-8S were bought by the Philippines, who incorporated them into the 7th Tactical Fighter Squadron at Basa Air Base, from which would intercept Soviet bombers and escort presidential flights. Meanwhile, the photo reconnaissance version of the Crusader continued in service in the U.S. well into the following decade, with the last operational unit turned over to the National Air and Space Museum in 1987. With a long and varied career, the Crusader's significant contribution to aviation history and the high regard in which it is held is perhaps best summed up through the famous message written on its pilot's insignia. Quote, "When you're out of F-8ES, you're out of fighters." Engineered by the visionaries behind the P-51 Mustang, the North American A-5 Vigilante was America's answer to the call for a supersonic nuclear bomber to dominate the skies during the Cold War. Epitomizing technological extravagance with its titanium-armored General Electric J79 turbojet engines, pioneering digital flight computer, and gold-plated engine bays, the Vigilante was a monumental gamble of raw speed and atomic devastation packed into a single 15-ton powerhouse of a warplane. Blasting off carrier decks with a thunderous 17,900 pounds of thrust per engine, this nuclear deterrence aircraft rewrote the playbook on speed and strength. Measuring a striking 76 feet nose to tail with a 53-foot wingspan, it carved through the heavens at a blistering 1,400 miles per hour. Equipped with advanced fly-by-wire controls, a bomb navigation system integrated into the pilot's heads-up display, and innovative features like adjustable engine intakes, the A-5 aimed to revolutionize Cold War aviation and show the world that thanks to America's ubiquitous carrier fleets, no target on Earth was beyond its cataclysmic reach. Yet its lavish gold plating and pioneering avionics also marked it as a potential financial sinkhole. Worse still, a radical shift in military strategy in the 60s put the Vigilante's very survival in jeopardy. Like the P-51 Mustang before it, the A-5 faced a critical crossroads. It either showed its worth or faced oblivion. The aviation world was on fire in the late 40s and early 50s, with breakthroughs and rapid advancements. North American aviation, the brains behind the iconic P-51 Mustang and B-25 Mitchell, dove headfirst into this wave of innovation, setting their sights on engineering a new type of plane never seen before. By the early months of 1954, led by Chief of Preliminary Design Frank G. Compton, North American aviation's engineers began brainstorming a new breed of bomber that could launch off aircraft carriers, break the sound barrier, and lug a hefty payload of nukes under any weather condition. This venture wasn't just the next chapter in the company's playbook. It was their chance to make a comeback after the flop of the North American XA-2J Super Savage. Back then, dreaming up a nuke-toting plane that could clock twice the speed of sound and still play nice with the cramped deck of an aircraft carrier was almost beyond belief. Nuclear bombers were flying fortresses that could not land on an aircraft carrier, but if the ambitious deed could be done, the U.S. could project its nuclear power across the globe like never before. Their design concept featured a dual-engine configuration, with the wings positioned high on the aircraft's fuselage, echoing the structural aesthetics of the XA-2J. However, it diverged significantly in its form factor, embracing a sleek, aerodynamically aggressive silhouette characterized by sharp angles and equipped with jet propulsion systems in place of propellers. The aircraft showcased a pioneering design, most notably through her slender nose section and cutting-edge air intake mechanisms. These intakes were lauded for their fully adjustable capabilities, marking a significant milestone in the design of supersonic bombers by optimizing airflow at various speeds and altitudes. Initially, the aircraft's stability framework proposed the inclusion of dual tail fins. However, this concept matured through iterative design enhancements into a singular, substantial, and adjustable tail fin, demonstrating a thoughtful design evolution to augment aerodynamic efficiency and control. The prototype was named the North American General Purpose Attack Weapon and quickly turned heads in the U.S. Navy. They laid down the gauntlet, insisting this bird should break Mach 2 and still launch from a carrier deck loaded to the brim, even on a day with no wind. Compton and his crew, against the odds, managed to hit those steep targets. By the summer of '55, North American Aviation got the green light to build a model. By the fall of 1956, they scored a contract to whip up 2 flying prototypes. The first one took to the blue on August 31, 1958, straight out of Columbus, Ohio. As the development advanced smoothly, the Navy's game plan for the plane took a bit of a turn. Initially driven by the Korean War's push for low-altitude conventional sorties, the Navy started eyeing this new warplane as a replacement for the Douglas A-3 Skywarrior, with a focus on carrying a nuclear punch. So, the design team packed in a bomb bay that was nothing short of a Swiss Army knife when it came to versatility. Ready for a nuke, extra fuel, or gear for spy missions. Mixing the old school with the new tech in one sleek package. The path towards mass production and combat service looked straightforward, but the situation was about to take a drastic turn. In the late 1950s and dawn of the 1960s, North American aviation caught on to the fact their brainchild could flip the script on combat flying. They rolled up their sleeves and dove into perfecting the ultimate version, the A-5B model. North American ditched the need for a zero-wind takeoff, a constraint limiting the aircraft's flexibility in various weather conditions, and incorporated a new humpback fuselage, allowing the A-5B model could carry more fuel. This modification was not merely cosmetic but functional, allowing the bomber to venture deeper into enemy territory or stay aloft longer for reconnaissance. The transformation extended to the wings, which were reimagined with larger flaps. This adjustment wasn't just a tweak, but a strategic overhaul that doubled the aircraft's range when equipped with external fuel tanks, like a bird of prey extending her wings to glide further and longer in search of her next target. Similarly, the A-5B, with her enhanced wings, could reach adversaries far beyond her previous limits. What unfolded was regarded as a miracle of engineering that shook the foundations of the combat aviation world to its core. When the Vigilante stepped onto the scene, she was not only one of the heftiest birds to grace the deck of an aircraft carrier, but hands down the most intricate. Using aluminum lithium alloy for wing skins and titanium for critical structures was also unusual for the era. Other exotic materials included a gold coating to reflect heat in key areas such as the bomb bay. The wings, vertical stabilizer, and nose radome were designed to fold to enable easier stowage onboard aircraft carriers. This powerhouse was juiced by a pair of General Electric J79 turbojets positioned far apart for better stability and performance. These engines breathed in air through specially designed inlets that featured adjustable ramps. Like a runner's nostrils, these ramps could open wider for more air when sprinting and narrow down for less air when resting, optimizing the engine's efficiency at different speeds and altitudes. The J79, a legend in its own right for powering iconic warplanes like the Convair B-58 Hustler bomber and the versatile McDonnell Douglas F-4 Phantom II fighter, was custom fitted into the Vigilante's core. Among these adaptations, the most intriguing was the inclusion of an air impingement starter system. This innovative mechanism deviated from conventional starting methods by directing high-pressure air at the engine's turbine blades. Like blowing on a pinwheel to make it spin, the air impingement starter worked on a similar principle, but on a much grander and more complex scale. The Vigilante's cutting-edge blueprint as a carrier-based supersonic nuclear bruiser showcased a twist in her weapon system, marked by her unique linear bomb bay between the rear fuselage engines. This clever setup let the aircraft drop her payload, usually a Mark 28 nuclear bomb, while blitzing at supersonic speeds, a feat that was nothing short of revolutionary at the time. When infiltrating into enemy territory, she could race through the sky, her sleek frame cutting a path at speeds faster than the speed of sound. Within her belly, nestled between the engines, lies the Mark 28 bomb, cradled by two disposable fuel tanks in a cylindrical bay, an arrangement known as the stores train. This design was not just about carrying a bomb, it was about integrating it with the fuel tanks in an efficient and tactical way for deployment in long-range missions. As the Vigilante approached her target, the fuel from these tanks would be consumed, lightening the load and preparing the bomb for release. Clinging to the tail end of the last fuel tank were fold-out fins, the key to keeping the bomb steady once it hit the open air. The release was as thrilling as it was exact. The spent fuel tanks and the bomb primed for delivery were shot out the back by a blasting drogue gun. This ejecting technique meant the bomb could be let loose clean and safe at breakneck speeds, keeping the plane out of harm's way while increasing the odds of a successful hit. On the drawing board, the A-5 Vigilante was a stunner, but all those trailblazing features quickly sent the budget into the stratosphere. Charging into action with Heavy Attack Squadron 3 in June 1961 at Naval Air Station Sanford, Florida, the Vigilante aimed to be the new top dog, stepping in for the Douglas A-3 Sky Warrior in the high-octane world of heavy attack, where the stakes were nuclear dominance. But the Vigilante's welcome to the fleet was a baptism by fire. Her avant-garde systems, though revolutionary, were green, leading to a slew of teething problems that tested the mettle of those who flew and maintained her. These advanced systems, while a leap forward, initially suffered from reliability issues, a reminder that pioneering technology often comes with its own set of growing pains. However, as the ground crew's expertise deepened, most of these challenges were ironed out, but it was too late. In what seemed an instant, the fate of the Vigilante was sealed. Despite her remarkable capabilities, the A-5 Vigilante hit some turbulence in the field. Her complex systems demanded extensive maintenance, complicating service and upkeep during sea deployment. The Vigilante's large size and limited range presented difficulties when operating on smaller aircraft carriers. Although innovative, the linear bomb bay proved unreliable during testing, with nuclear weapons often failing to separate cleanly from the aircraft. As strategic priorities shifted in the early 1960s, so did the A-5 Vigilante's role. The military was all in on intercontinental ballistic missiles, or ICBMs, for its nuclear playbook, sidelining bombers like the Vigilante, which was gunning to be the protagonist in sea-based nuclear strikes. Despite spending vast resources making it a nuclear powerhouse, the plug was pulled on the project after just a half-year in the fleet. Shifting gears from nuclear deterrence to the cunning game of espionage and electronic warfare, the Vigilante embraced a new identity: the RA-5C. This recon wizard came loaded to the gills with high-resolution cameras and state-of-the-art electronic espionage gear, making it an intelligence-gathering powerhouse during the thick of the Vietnam War. The RA-5C variant of the Vigilante spread her wings, both literally and figuratively, with an expanded wing area and a distinctive canoe-shaped fairing slung under her belly, crammed with an arsenal of surveillance tools. Radar, infrared scanners, cameras, and cutting-edge electronic countermeasures made her a fearsome eye in the sky. Even as she morphed into a reconnaissance powerhouse, the RA-5C kept her bomb bay doors, ready to switch gears back to a weapon of war if push came to shove. Thankfully, that day never dawned, amped up with even more robust engines. This bulked-up yet blisteringly fast edition sacrificed a touch of nimbleness for a whole lot of muscle and reliability. Though her time-dominating seas was more a sprint than a marathon, the A-5 Vigilante's mark on naval flying is legendary. She played a pivotal role in driving the tech and design philosophies that would pave the runway for future fighters and spies in the sky for decades. The Vigilante became a glimpse into tomorrow, with her top-tier avionics and trailblazing stealth technology inspiring the likes of the F-117 Nighthawk and B-2 Spirit. Now, the A-5 Vigilante takes her well-earned place in museums, standing as a monument to American ingenuity and the relentless push for the upper hand during the Cold War. The Convair F-106 Delta Dart is often called the ultimate interceptor. Created in the 1950s as a robust response to the growing threat of attack by Soviet bombers, it soon made its mark at the heart of the United States Air Force's interceptor fleet. Nicknamed the Six, its revolutionary design included a contoured Coke bottle shape, delta wings, and highly advanced avionics, making it a fearsome opponent for enemy aircraft day and night, whatever the weather. What's more, its potent Pratt & Whitney J75 engine boosted the F-106 to the supersonic realm, leading it to break the world speed record in 1959. In its later years, it still stood as a pinnacle of Cold War aerospace engineering, and even went on to join the ranks of NASA. Through the 1980s and 90s, it took part in a series of cutting-edge experiments, a fitting end for the remarkable career of the Six. The F-106 was developed as the final incarnation of the U.S. Air Force WS-201A project, which had begun in 1949 with the objective of creating a new supersonic interceptor aircraft by 1954. In 1951, the Air Force had initially selected an earlier Convair design, the F-102, but the prototype's performance turned out to be a disappointment, with the aircraft limited to subsonic speeds and relatively low altitudes. However, by 1953, Convair had identified an opportunity to improve its design using the brand-new aerodynamic principle known as the area rule, formulated by NASA engineer Richard Whitcomb the previous year. According to this concept, the cross-sectional area of an aircraft should change smoothly along the length of the aircraft in order to minimize sudden changes in shape, which could cause increased drag and resistance at high velocity. Therefore, in order to conform to the rule, the F-102's fuselage was reshaped to have a Coke bottle or wasp waist contour, which would allow it to cut through the air more quickly and efficiently, while modifications were also made to the aircraft's engine, avionics, and weapons. Although the redesigned F-102 was now able to break the sound barrier, it could do so only marginally. What's more, not only did it become evident that the aircraft struggled to sustain such speeds, but there were concerns about its performance at high velocity, particularly its maneuverability and fuel consumption. Yet, with time of the essence, the Air Force gave the go-ahead for the aircraft's production despite its deficiencies, becoming the F-102A Delta Dagger, commonly known as the Deuce. Meanwhile, Convair continued its efforts to build a more adept interceptor, focusing on the creation of the F-102B. An extended production contract for 17 F-102Bs was given to Convair in April 1956. 2 months later, it was redesignated the F-106, giving it the distinction of being the second highest sequentially numbered P or F aircraft to enter service under the old numbering sequence used by the U.S. Air Force, with only the F-111 being higher. This sequence was later changed with the introduction of the 1962 United States Tri-Service Aircraft Designation System, which streamlined the naming conventions across the branches of the military. For this new aircraft, Convair abandoned the Pratt & Whitney J57 engine used in the F-102A in favor of the more powerful J75, which provided an impressive 4,500 pounds of thrust with an afterburner. This allowed the F-106 to break the sound barrier far more comfortably than its predecessor, with a top speed of Mach 2.3, or approximately 1,525 miles per hour, or 1,325 knots at high altitudes, making it far more effective at intercepting enemy bombers. While accommodating this engine would necessitate a larger airframe, this would come with its benefits. Firstly, it enhanced the aircraft's structural integrity, which is crucial for withstanding the stresses associated with supersonic speeds and aggressive maneuvering during interceptions. Secondly, it provided a broader platform for the F-106's delta wings, so-called because of their triangular shape resembling the Greek letter delta. This increased the wing area, which in turn increased lift, particularly beneficial at the high altitudes where interceptors typically operate, as the air density is lower and generating sufficient lift becomes more challenging. It also meant larger control surfaces on its wings, with larger ailerons and elevons that provided more responsive and effective control during high-speed maneuvers, where precise and quick adjustments are needed to maintain or change the flight path. Moreover, Convair's design team took the new airframe as an opportunity to further refine the fuselage's shape, enhancing its aerodynamic efficiency. Building on the F-102A's application of the area rule, they made more precise adjustments to the fuselage contours, not just at the wings but along the entire length of the aircraft, aiming to further smooth out the changes in cross-sectional area, and thereby reduce aerodynamic disturbances even more effectively, especially at transonic and supersonic speeds. The larger airframe also gave the F-106 space to incorporate more advanced avionics systems, representing a vast improvement over those used in the F-102A. As the aircraft's main role would be shooting down enemy bombers, it was given a state-of-the-art all-weather Hughes MA-1 fire control system that combined several functions such as automatic search, track, intercept, and missile guidance into one integrated package. This groundbreaking feature allowed the pilot to focus on flying the aircraft while the system handled target tracking and weapon deployment. The F-106 was also equipped with the AN/ASG-18 radar, which was more advanced than the MG-10 system used in the F-102A. This radar had longer detection ranges and better tracking capabilities, being the first U.S. radar system capable of lock-on and track while scan, allowing it to engage one target while continuing to search for others. Meanwhile, the aircraft's inertial navigation system, or INS, was capable of providing crucial accuracy for long-range interception missions. It helped maintain the correct course, altitude, and speed during engagements. The F-106 integrated digital computers to process radar data and flight parameters faster and more accurately, facilitating better decision-making during high-speed interceptions. As it had no guns or provision for carrying bombs, the primary weapons of the F-106 were its air-to-air missiles. The aircraft typically carried 4 Hughes AIM-4 Falcon missiles, which included infrared or heat-seeking missiles as well as radar-guided versions in order to be able to engage targets effectively day and night and under a variety of weather conditions. These missiles were compact and designed specifically for interceptor aircraft, providing the F-106 with versatile engagement options against enemy bombers and fighters. Unique among its contemporaries, the F-106 could also be armed with the AIR-2 Genie unguided nuclear rocket, an extraordinary armament intended to provide a last resort capability against formations of enemy bombers. The Genie was equipped with a 1.5 kiloton nuclear warhead, capable of destroying multiple aircraft within its blast radius, reflecting Cold War-era doctrines that anticipated large-scale bomber attacks. Another feature that significantly enhanced the F-106's operational effectiveness, particularly in its role as a continental defense interceptor, was its in-flight refueling capability. This enabled it to remain airborne for longer, allowing it to patrol sensitive airspace or remain on station while waiting for potential threats. During the Cold War, this was considered vital, as quick response times to intercept potential Soviet bombers were critical for national defense. It also meant that the aircraft was not limited by its initial fuel load, allowing it to cover much larger areas during its patrols, ensuring broader coverage and quicker response times across larger defensive zones. Indeed, during periods of crisis, in-flight refueling could keep F-106s in the air almost indefinitely, as long as other logistical and pilot fatigue factors were managed. This non-stop deployment capability was crucial for maintaining a constant defense posture. Furthermore, by maximizing the time spent airborne per sortie, in-flight refueling helped optimize the use of resources, including the wear and tear on aircraft and the logistical demands of multiple takeoffs and landings. When it came to safety, the F-106 boasted a unique provision. Instead of a standard ejection seat, it featured a full escape capsule system. When activated, the entire cockpit area around the pilot, including a portion of the canopy and instrument panel, would eject as a whole from the aircraft. This system was intended to protect the pilot from the extreme conditions associated with high altitude and high speed ejections, such as severe wind blast, extreme cold, and a lack of oxygen. The capsule was equipped with its own environmental controls to provide breathable air and maintain a survivable temperature until the pilot descended to a lower altitude or was rescued. While the base of the capsule included impact-absorbing materials and devices similar to airbags that would help cushion the landing and minimize the risk of injury to the pilot. On December 26, 1956, at Edwards Air Force Base in California, the initial prototype of the F-106 made its maiden flight, followed by a more fully equipped second prototype exactly 2 months later. However, testing during this period revealed disappointing results. The aircraft's acceleration and top speed did not meet Convair's expectations and showed minimal improvement over the F-102. Additionally, issues with the engine and avionics systems led to reliability concerns. These problems and the delays they caused almost led to the cancellation of the entire program. Nevertheless, despite the initial setbacks, the Air Force decided to continue with the F-106 program, largely due to strong support from the Air Defense Command. Based on the test results, officials were optimistic that modifications to the inlet duct cowling and charging ejectors would enhance both the acceleration and speed of the aircraft. These changes were planned after Category 2 testing and would be assessed during Category 3 testing. In an effort to speed up development and move towards production, the service took several decisive steps in April 1957. Including the conditional acceptance of several F-106S from Convair that were still being used for flight testing. Additionally, the Air Force made quick decisions to resolve outstanding development issues. By mid-1957, funding was secured for 120 F-106As. Eventually, the USAF placed an order for 350 F-106s, significantly less than the initially planned fleet of 1,000 aircraft. The delivery of the single-seat F-106A and the twin-seat F-106B, which is a combat-capable trainer variant, started in October 1959 to 15 fighter interceptor squadrons. The F-106 entered service on June 2, 1959, joining the 498th Fighter Interceptor Squadron based at Geiger Field, Washington. Though officially named the Delta Dart, this was rarely used, with most referring to it by a different moniker, the Six. Soon enough, it had become the primary all-weather interceptor of the U.S. Air Force, eventually serving across the contiguous United States, Alaska, Iceland, Germany, and South Korea. The F-106's exceptional speed made it the clear choice for the USAF when selecting an aircraft for its attempt to set the world absolute speed record, a project known as Project Firewall. Sure enough, on December 15, 1959, it hit the headlines when Major Joseph W. Rogers achieved the record while flying an F-106 at 1,525.96 miles per hour at 40,500 feet. However, it wasn't all good news in the Six's early days. The aircraft soon encountered various technical hurdles, including issues with generators, fuel flow problems in cold weather conditions, and malfunctions in the combustor starters. In December 1959, a serious incident where the canopy of an aircraft was accidentally jettisoned mid-flight led to the temporary grounding of all F-106s. Thankfully, by the start of 1961, many of these issues had been addressed, thanks in part to two major modification and retrofit programs implemented during that period. And from then on, the aircraft's outstanding performance began to be recognized and appreciated by its pilots, boosting its popularity among them. Before long, it had staked its claim at the heart of the U.S. Air Force's interceptor fleet, its cutting-edge technology and superior performance leading to the phase-out of older aircraft models that had previously filled the air defense role, such as the North American F-86 Sabre and the Northrop F-89 Scorpion, which were now rendered obsolete. While the Six was never used in overseas combat, it provided the United States with a robust defense against the threat of the Soviet Union and its allies at the height of the Cold War. With growing paranoia about the possibility of enemy bombers dropping a nuclear payload on the American mainland, the F-106 stood as a proud guardian, ever ready to see off the communist menace. As evidence of the aircraft's preparedness, one notable and intriguing incident occurred on February 2, 1970, when Captain Gary Faust, flying over Montana in an F-106 from the 71st Fighter Interceptor Squadron, found himself in a flat spin. Adhering to protocol, Captain Faust ejected from the aircraft. Astonishingly, his exit shifted the aircraft's balance enough that it stabilized itself, subsequently landing wheels up in a snow-laden field with only minor damage. This aircraft earned the nickname the Cornfield Bomber and was transported back to base via rail. After repairs, it returned to service and is now proudly displayed at the National Museum of the United States Air Force. By 1972, the F-106 was beginning to look a little dated, and a significant upgrade program known as Project 6 Shooter was initiated. This aimed to enhance the aircraft's operational capabilities and extend its service life by addressing some of the limitations in its original design. One of the major modifications was the replacement of the original canopy, which had metal bracing, with a new, all-clear canopy that lacked these braces. This change significantly improved pilot visibility, which is crucial for situational awareness during flight operations, especially in complex air-to-air combat scenarios. Alongside the canopy upgrade, the project also included the installation of an optical gun sight and provisions for an M61 Vulcan 20mm rotary cannon. This cannon was integrated into the aircraft's center weapons bay, equipped with 650 rounds of ammunition. The addition of the Vulcan provided the F-106 with a conventional gun armament, offering more versatility in combat engagements, particularly in scenarios where missile armament might not be ideal. Even with these changes, inevitably, the F-106 was eventually superseded by newer aircraft. By 1981, the F-106 began to be phased out of frontline service with the introduction of the more advanced F-15A Eagle, which offered superior agility, avionics, and overall combat capabilities, marking the next generation of air superiority fighters. Some former Air Force F-106s were passed on to Air National Guard units across the country, who used them for various defensive and training roles, until they, too, retired the last of their sixes in 1988. Starting in 1986, 194 retired F-106s were withdrawn from storage at the Military Storage Disposition Center in Arizona and converted into unmanned target drones for the Pacer 6 program by the Aerial Target Squadron until the last was destroyed in 1998. Another user of the F-106 during its later years was NASA. While it acquired several F-106s for various research projects, perhaps none was more famous than the one nicknamed the Lightning Strike Plane. As part of a NASA investigation, it was incredibly struck by lightning 714 times without sustaining damage. In one particularly notable experiment in 1984, the aircraft was struck 72 times during a single hour-long flight at 38,000 feet. A key modification for these experiments was replacing the composite nose radome with a metallic one, which was essential for safety during the lightning tests. Although the F-106 could reach speeds of Mach 2.3, for these lightning experiments it flew at subsonic speeds of 300 knots, or around 350 miles per hour, at altitudes ranging from 5,000 to 40,000 feet. The aircraft was also equipped with optical sensors, including a video camera and a light detector, while data acquisition was carried out using digital waveform recorders that were considered state-of-the-art in the 1980s. In another innovative project called Eclipse, which ran from 1997 to 1998, NASA used 6 F-106 drones at the Dryden Flight Research Center. Project Eclipse aimed to demonstrate the feasibility of an Aerotow launch vehicle. It involved towing a modified QF-106 aircraft in flight with a C-141A transport aircraft. This test successfully showed that it was possible to tow and launch a space launch vehicle from behind a tow plane, opening new possibilities for aeronautical and space research applications. Over the decades, the F-106 has dominated the skies and significantly shaped modern air defense capabilities, leaving an enduring legacy that continues to influence the strategic and technological frameworks of today's air forces.